Hello, everyone. Welcome to MetaGate. And today we are starting our iron making crash course or the one shot lecture on iron making. So, sorry, this is steel making. I'm sorry. Just a minute. It's like this. Yeah, yeah. Yes. So, welcome to steel making class. So, today we will basically we'll see the subject and the subject of steel making. And in this class, we will cover it entirely according to the requirement of the examination, upcoming examination, which is the sale exam. So first and foremost, let us start the class with uh, by focusing on what is steel. What is meant by steel? If I ask you that what is steel, so you will say that steel is nothing but it is the interstitial solution of carbon in iron, right? So we can say that steel is an interstitial, it is an interstitial solution of carbon in iron, right? But see, obviously carbon will be there in the interstitial sites, right? But apart from carbon, there are some other elements which are also present in steel. So what are those other elements? There will be some other elements as well which will be present. So these elements are going to be like manganese, sulfur. Okay, we'll have traces of sulfur also, phosphorus, etc. So this will be present. Okay, and why steel is such an important material? Okay, if I kind of talk about steel, then why steel is so important? Because steel is important because, okay, it has, when we add the carbon in iron, okay, it increases the strength. Okay, by addition of carbon in iron, what happens is the strength increases. Strength increases, not only the strength increases, along with the strength, okay, the hardness also increases. So both the strength and the hardness increases. So properties of steel, I can say that the properties of steel are excellent. So that makes the steel a very good engineering material. So you have excellent toughness. You have excellent toughness. Okay. And you have good strength to weight ratio, which is very, very important for engineering application. You have very good strength to weight ratio. Okay. You have good thermal stability. So that means uh, at high temperature also, it can be used comparatively at higher temperature or even at lower temperature. And it is also very ductile. Okay, it has got good amount of ductility also, and it is less brittle. So all these things make steel really a very good engineering material. Now, that is all right. But now we will be focusing on the roots of steelmaking. So we'll be discussing in today's class that what are the different routes that are basically available to us. And then we will be studying these routes in details. So roots of steelmaking. So if I talk about the roots of steelmaking, right? So the first route is what? It is basically pig iron based steel making. Okay, so we can call it pig iron based steel making route. This is pig iron based steel making route. So you will have, so what are the steps that we follow here? So in the pig iron based steel making route, we will take the iron ore. Okay, the iron ore is directly charged into the blast furnace. This is basically iron making. So iron ore is charged into the blast furnace. And after that, what happens by the iron making route? We produce the pig iron. The pig iron is basically produced. Okay. Now the pig iron contains, what is the composition of this pig iron? The pig iron contains, it contains about 4% carbon. Okay. It contains high silicon and manganese. Okay. And there are certain impurities also. There are certain impurities also. The impurities that will come inevitably. And what are the impurities? The most deleterious or the most uh, dangerous impurity in the pig iron, I should say, it is sulfur. Because we will see that this sulfur removal is really something which becomes very, very difficult. Okay, as far as the in the steel making process also. So we'll see that. Okay. Now, in step two, what we do in step two, if I talk about step two, so this pig iron that we talked about, okay, this pig iron is basically charged in the BOF or the LD converter. So BOF stands for basic oxygen furnace. Basic oxygen furnace, right? So or the LD converter. And here, what happens? Pure oxygen is blown, right? So in the BOF process, pure oxygen is blown. And because as we are blowing pure oxygen, the carbon oxidizes. So you see, what happens is that in the iron making process, we have studied that what are we using in the iron making process? We are predominantly, so what is our reducing agent in the iron making? In the iron making, predominantly our reducing agent is the coke. And it is in the the atmosphere that is there in the iron making in the entire blast furnace. So that is basically our reducing atmosphere, and we are using coke. So a lot of carbon is getting inside the pig iron. So that is why the pig iron, the carbon percentage is quite high as far as the concentration of the carbon is concerned in the pig iron. Now in the steel making process, we need to oxidize this carbon, whatever carbon is in the melt or in the pig iron, because if we get that amount of carbon, then we cannot call it steel. So that will not be steel, right? So we need to remove the carbon. Whatever carbon has gone into the pig iron, now in the steel making process, we need to remove that carbon, right? So basically that is why oxygen is used. So you should know one thing, that steel making is nothing but it is a oxidizing process. So the atmosphere in the steel making is oxidizing. So basically because we are using oxygen in the steel making process. And apart from carbon, other elements are also getting oxidized, like silicon, manganese, we'll see all this, phosphorus, they also oxidize and go into the slag. So they also oxidize and go into the slag. So that part is always there. So this is the basic oxygen steel making. And another route that we have is basically what we call the DRI route. And what is the DRI route? That is called the direct reduced iron. DRI here stands for direct reduced iron. So please focus on the abbreviations also. Sometimes directly questions come from the abbreviations that what DRI stands for. So now that in the DRI route, what we do? In the DRI route, basically we take the iron ore or we take the ore and it is reduced in solid state. It is just reduced in solid state. And what happens after that? This gives us basically sponge iron. This gives us sponge iron. So this is basically DRI. The sponge iron, we are calling it as DRI or the direct reduced iron. And then it is melted in the electric arc furnace. So this sponge iron that we have got, this is basically melted in electric arc furnace or EAF. Okay, so EAF is nothing but electric arc furnace. So this is melted in electric arc furnace. Okay, and scrap is also used. Electricity is used here and scrap is used. Scrap and electricity is used. Right? Now we will be seeing some of the old steel making processes. We'll just overall discuss and then we will start our main topic. So if I talk about the old steel making processes, now first steel making process that I should talk about is the Bessemer process. So if I talk about the Bessemer process, you see what happened in the Bessemer process. In the Bessemer process, suppose this is my converter. Converter means where I am putting the hot metal for the oxidation. Okay, so this is the converter. Now, at the base of the converter, I am talking about the Bessemer process. At the base of the converter, these were called the TUFs. TUFs. So from the TUFs, actually air was blown. So air was blown. Air. Right? So air was blown inside the TUFs. And in the converter, there was what was there? There was basically inside the converter, there was the hot metal. So we have this is the hot metal, right? This is the hot metal inside. Okay. And we are blowing air. We are blowing air. Now, what is this air going to do? This air will have, obviously, air has oxygen. Okay. So the oxygen of the air, it is going to oxidize the carbon and other elements like silicon, manganese, phosphorus. Okay, all these things will eventually get oxidized. Okay, this will get eventually oxidized, right? Inside the uh, converter or inside in the Bessemer process. But you see here, obviously we are using air as the oxidizing agent. So you can say that in the Bessemer process, air is used as oxidizing agent. So air is used as the oxidizing agent. Now, when we are using the air as the oxidizing agent, then what is happening? Air, we know that air is not pure oxygen. A lot of hydrogen is also there in the air, right? So a lot of hydrogen is inevitably there, okay, in the air. So what will happen? So a lot of nitrogen is also there in the air. So what is going to happen is that no pure oxygen available. We can say pure oxygen is not available. And as air is having a lot of nitrogen, so N2, that is the nitrogen, will get into the melt, right? It will get into the melt. And the amount of nitrogen in the melt will increase definitely because we are using air here. So the amount of nitrogen in the melt will increase. So the nitrogen is not something which is good for steel. So this makes the steel brittle. Okay, nitrogen inclusion, right? So nitrogen is not good for steel. And this was one of the problem in the Bessemer process. Now, Henry Bessemer, this process was basically called Bessemer process because it was started by Henry Bessemer. Now, Henry Bessemer himself also understood that there is this problem, but still he had to go with this process. Why? Because you see, at that time, the process of separating the oxygen from the air, that was not available. So he had no other option but to go for it. Now the Bessemer process was improved by Thomas, and it is called Thomas process. Now we will talk about the Thomas process. What is Thomas process? Thomas process is sometimes also called basic Bessemer process. This is also called basic Bessemer process. Okay. So this is also called basic Bessemer process or modified Bessemer process. So what happens here? Here, this is the same thing. Okay, the same thing is basically used, but here what we will be using here in the Thomas process, the lining, see if I am talking about the converter, if I am talking about the converter as well, this is the converter. So in the Bessemer process, the lining of this converter was acidic. But in the Thomas process, the lining is basically basic. So the lining is basically basic lining. And the slag basicity, as the lining is basic, I'm talking about the lining. So it is like dolomite or MgO, okay, or CaO, that kind of lining we are basically using, which is nothing but basic lining. So if the lining is basic, definitely the slag has also the slag has to be basic only. So the slag basicity is more than one. So we have seen what is meant by the basicity of the slag. It is nothing but the ratio of the basic oxides divided by the acidic oxides. So basicity more than one means your slag, basicity more than one means that your slag is basically basic slag. So the slag basicity in case of Thomas process, the slag basicity is more than one. We can say this, right? It is used when, and why this Thomas process is important? It is used when more phosphorus is present and comparatively, if in the hot metal, the more phosphorus is present, then the phosphorus removal, okay, will become easy if my slag basicity is more than one. That means if the slag is basic slag, phosphorus removal is going to become easy, right? So we will discuss all these things in more detail. So no worry about it. So it is used when you can just write, it is used. So this Thomas process is very good when phosphorus, okay, phosphorus in the hot metal is more. When phosphorus in the hot metal is more. The slag is mostly basic here. The lining of the vessel is also basic. So you can write the lining of the vessel is also basic. So we have basic lining. Now, why we are actually maintaining basic lining here? Because you see, when our slag is basic, suppose this is the hot metal. Now on the top of the hot metal, there will be slag. And suppose this is the slag on the top of the hot metal. Suppose this is the slag on the top of the hot. Now, right, this is like this. So this is the slag. Now, if the slag itself is acidic and the lining is basic, then what is going to happen? The acidic slag will attack the basic lining and it will eat up the lining, means corrode the lining. So the lining will get damaged, obvious. So the idea is if the slag is basic, you will have to have a basic lining. Okay, and in Bessemer converter or in in Thomas process or the basic Bessemer process, we are actually using this, right? Now, both the Bessemer process and the Thomas process, they are basically called the pneumatic steelmaking process. Why? If I talk about pneumatic steelmaking process, pneumatic steelmaking process. So what is meant by the pneumatic steelmaking process? Pneumatic steelmaking processes are those processes where we are directly using air or oxygen as the as the oxidizing agent. Okay, as the oxidizing agent, we are using the air or the oxygen. So in case of Bessemer in case of Bessemer process, as well as in case of Thomas process, in both the process that we have discussed, in Bessemer process as well as in case of Thomas process of the steel making, oxygen or air is blown from the tuyeres. Oxygen or air was blown, right, from the tuyeres. Tuyeres were beneath. So at the bottom, we saw that. So it was blown at the tuyeres at the bottom and complex conventional current takes place. Okay. So what happens is, see, suppose if this is the converter, okay, and these are the tuyeres we are having. Now we are blowing air, okay, inside. Now this is the melt. Now when air is going to be blown, obviously it will make some convectional current, obviously. So that is the melt is going to, okay, get circulated now, will get stirred now. That is exactly what we mean by complex convectional current. And you see the stirring of the melt. So here, as we are basically using the tuyeres and through the tuyeres we are blowing the air or the oxygen. So continuous stirring of the melt is also taking place. So obviously the oxygen from the air, it is oxidizing the impurities. That is one thing, and that is the most important thing which we try to achieve. That is the creating the oxidizing atmosphere. But apart from that, apart from creating the oxidizing atmosphere, the melt is going to be constantly stirred. The melt is going to be constantly stirred, which is also very, very important, right? Now we have another process which is called, this is not much used now, but this process was called the open hearth process. Open hearth process. Now, if I talk about the open hearth process, Okay, now you see the open hearth process, it was a slower process. And there is no, basically in the open hearth process, no oxygen injection is taking place. So we are not injecting the oxygen directly. So there is no oxygen injection, okay, in the open hearth. So then you can ask that, okay, if we are not injecting or if we are not blowing oxygen or air, then what is the source of the oxidation? Okay, which is the oxidizing agent now? So you can say that in the open heart, what we are using is the oxidizing agent is basically iron ore. It is basically FeO. So FeO is my oxidizing agent. Okay, that is the open hearth process, right? Where our main oxidizing agent is nothing but FeO. So iron is FeO is providing the oxygen, which is oxidizing the other things, okay, other impurities like carbon and all. But you see, there is some problem with the open heart. Say, for example, when I talk about the Bessemer process or the, you see, what we call the Thomas process, these are all autogenous processes. Autogenous processes. What does autogenous process mean? This is very important concept. What does autogenous process means? Autogenous means that you do not require any external fuel. We do not require any external fuel to keep this process going. Okay, this process will go by themselves. Why? Now the question is why? Because you see, when we are blowing oxygen or air, so a lot of oxidation reactions are basically taking place inside the converter. Okay, so lot of oxidation reactions are taking place. Say for example, carbon is getting oxidized and it is forming CO. Okay, likewise, I can say that manganese is getting oxidized into Mn. Okay, likewise, I can say that even phosphorus is getting oxidized to P2O5. Okay, I can say that silicon is getting oxidized to SiO2. So these are all happening inside the converter when I am blowing oxygen, right? All these reactions are basically exothermic reactions. Oxidation reactions are exothermic reactions. Exothermic means that they give up a lot of heat. So because these reactions are taking place inside the converter, and I am directly blowing oxygen or air inside the converter. So these oxidation reactions are also taking place at a comparatively faster rate because oxygen is directly available for the reaction. Oxygen is getting dissolved in the melt and it is being taken up by the impurities like manganese, silicon, phosphorus. They are directly taking up the oxygen from the melt. Okay, and they are converted into their metal oxides, and they are after converting into the metal oxide they are getting into the slag phase. Okay, they are getting into the slag phase. So in the process a lot of heat is going to be generated, so which makes the process itself autogenous process. But this kind of thing is not happening in the open hearth process. Why? Because you see what is happening in the open hearth process. In the open hearth process we are not using oxygen directly. So we are not using oxygen directly in the open heart. Rather, we are using FeO as the oxidizing agent. So and also there is very little bath agitation. Very little bath agitation. There is very little bath agitation in the open heart. So which makes it even more slow. The process is becoming very slow. So process is very slow. And apart from that, there is another problem as far as open hearth process is concerned. That is, the process is slow, and also uh, it is not always autogenous also. Autogenous means that, see, because here that much of heat is not generated. If I am blowing directly oxygen and direct oxygen is combining with the impurities and it is oxidizing the impurities, a lot of heat is generated. But in this process, that amount of heat is not generated. Okay, so this process is also not autogenous, not an autogenous process. So sometimes direct questions comes like this, that which of the following processes are autogenous processes, and options will be given to you. So please understand that and remember what are the autogenous processes. So first you need to understand which processes what are called autogenous processes, and then I have already told you the reason. Okay. So if I talk about the modern steelmaking process, modern steelmaking overview. So you will see that about 60% of the steel, of the total steel produced, I am talking about 60% of total steel is being produced by the BOF, basic oxygen furnace, or this is also sometimes called as LD. Okay, so we'll see what this is. This is extensively used. Okay, and it also has a lot of advantages. We will also see what are the advantages of these processes. 34% of the total steel, okay, is comes from the electric arc furnace. Here, electric arc furnace is also good process, but here the production, uh, the amplitude, or I can say the magnitude of the production is less. So LD process or BOF process can produce a lot of steel, but that amount of steel we will not be able to produce in the electric arc furnace. Another problem with the electric arc furnace is there has to be continuous supply of electricity. From the name on also only it is suggesting that electric arc furnace means there has to be continuous uninterrupted supply of electricity. So it is also very costly at times. Okay. And 6% comes from induction furnace, open hearth furnace, and things like that. 6% of total steel basically comes from open hearth furnace. So open hearth, because of its demerits that also we have discussed, has become more or less obsolete. Okay. Now, now we will basically see the now we will basically see the BOF or the LD process. We'll talk about the LD process in detail also, but let us take an overview about this process, LD process. Like now, let us understand this. So if I draw the converter, this is called the LD converter. It is a pearl shaped. It is spear shaped converter. And what happens in this BOF process is there is a lance. There is a lance, something like this. And this lance, what you call this lance? This lance is called oxygen lance. This is the oxygen lance. So from this oxygen lance, actually what we are doing, we are blowing in oxygen inside. Okay. And this is the hot metal. There is hot metal. Okay. And we are blowing in oxygen inside. And this oxygen which is being blown this oxygen is at very high speed, which is called supersonic speed or jet speed. Okay. So this oxygen is blown at a jet speed or supersonic speed. So very, very high speed. Now, when this oxygen is coming in contact with this melt, this oxygen will immediately, some part of this oxygen will get dissolved. It is going to get dissolved in the melt. Okay. A portion of the oxygen is going to get dissolved in the melt immediately. And what will happen? It will start oxidizing the impurities. It will start oxidizing the impurities. Okay. Okay. Now, apart from that, this is there in the BOF. Now, this is the main idea of the BOF I have told you. Now, what are the feed? That feed means what are the feed means? What are the which are the things that we are actually charging in the BOF or the LD converter? So the feed is our liquid pig iron, scrap. We can also charge the scrap, lime, because you see this process is basically basic process only. So we'll add lime, and obviously oxygen is there. Oxygen is we are actually supplying through the lungs. Okay. And so if this process is basic, what should be the lining of the converter? How should be the lining of the converter? Obviously, the lining of the converter should be basic only. Lining is basically basic, right? So this is the main uh, thing which is there. Now, sometimes this process has also been improved nowadays. What happens? How we have improved the process? See, oxygen is basically when the oxygen is uh, passed through the hot metal in a very high speed, which we call the supersonic speed, then oxidation reaction is taking place. Everything is all right. But when this oxygen is actually impacting this hot metal, maybe the hot metal which is basically down here, okay, yeah, fit down here, this side, that part will not get oxidized. It may take place. Okay, uniform oxidation sometimes may not happen. Then why uniform oxidation may not happen? Because if there is improper stirring of the hot metal, if there is improper stirring of the hot metal, then uniform oxidation may not happen. In order to uh, increase this stirring, nowadays what is done is that through the tweezers we are nowadays blowing uh, what we call argon. Argon gas is basically blown through these 2 years. Argon gas. So you see, argon is what kind of? Argon is a noble gas, right? So as argon is a noble gas, this will not take part in any of the reaction, but it will help in stirring the hot metal. It will help in continuous stirring of the hot metal. So you see, we will discuss if the hot metal is stirred. Number one, it has a very, very good effect. So argon stirring, you can write argon stirring, how it helps. So the argon stirring, it improves, like I can say first, it makes the temperature of the hot metal uniform. So the temperature of the hot metal, it becomes uniform. So it makes the temperature, it makes the temperature of the hot metal uniform. So it becomes basically uniform. Second, what happens? Uh, you can say that proper mixing is taking place. Proper mixing is taking place. So that means the reaction is uniform throughout the hot metal. So all these things are basically happening because of the stirring, argon stirring, right? Right. Now, we have discussed these things. Now we will see that if I draw the converter, so this is our converter, and this is the oxygen lungs. I'm talking about BOF, basic oxygen furnace. Okay. I'm talking about the BOF or the basic oxygen furnace. Okay. Or the LD converter. It's the same thing, right? Now you see, there is the oxygen lancing. So oxygen we are blowing from here. This is the hot metal. This is the hot metal, right? Now, this hot metal will have a lot of impurities. What are the impurities? That will carbon we will not call impurities, but yes, carbon is also, what is the percentage of carbon in the hot metal? It is 3.5 to 4%. Okay, but that much of carbon is not desired in steel. Okay, so what you will do, right? The carbon, so crude steel, in crude steel, the carbon percentage should be less than 0.1 weight percent. Oxygen, it should be 400 to 600 ppm. Sulfur, it should be 0.02%. Phosphorus should be very less, 0.008%. Okay, I'll write down. So carbon is there. Apart from carbon, silicon is there. Okay, manganese is there, and phosphorus is there. Now you just see that what is the composition that we would like to have in crude steel. Crude steel means, see, there has to be more refining. But in the primary steel making process, after the primary steel making process, we will go for the secondary steel making process. In the secondary steel making process, there is going to be more refining. We will see that why we have to go to the secondary steel making process. There are certain impurities which we cannot basically remove much in the steel making process. One such impurity is sulfur. So sulfur is there, and sulfur inclusions, or if the sulfur is there in the hot metal, we cannot remove much of the sulfur by the primary steel making process. Okay, so then we have to go for the secondary steel making process where the sulfur is basically removed by the RH degassing system. So we will see that. Now, in the crude steel, what happens? What is the composition of the crude steel? So I can say that the composition of the crude steel, the carbon has to be less than 0.1 weight percent. Okay, carbon has to be less than 0.1 weight percent. Oxygen, it should be around 400 ppm parts per million to 600 ppm. That must be the oxygen. Okay, sulfur, it should be 0.02%. This is sulfur. Phosphorus should be very less, like I said, 0.008%. This is phosphorus. Silicon should be also less, which is, I can say, 0.1%. And nitrogen should be 40 to 80 ppm. So this is the this is mainly the composition of the crude steel. Now we will see that what happens when oxygen is blown. Okay, what happens when oxygen is blown? When we are blowing oxygen, so we have carbon, silicon, phosphorus, manganese, all these in the hot metal. And then we start blowing oxygen. Then we start blowing oxygen. Now, when oxygen is blown, all these elements, they have affinity towards the oxygen. all these elements, they have affinity towards the oxygen. Affinity means attraction. Okay. So they will react with the oxygen that is being dissolved in the hot metal. Like silicon is going to react and it is going to form SiO. Now, once silicon from the hot metal, this silicon was in the hot metal. So I can write HL. Let us write in. So silicon, I can say this is in the hot metal. So HL plus the oxygen, the dissolved oxygen. Okay. So it will form SiO. And this silicon, SiO2 silica, is going to get into the slag. It will go into the slag. Likewise, manganese, Mn, manganese from the hot metal. Okay, it will take up the oxygen dissolved in the hot metal and it will form MnO. And this manganese oxide will go into the slag. Okay. Similarly, phosphorus. Phosphorus from the hot metal, what will happen? It will take up the oxygen and it will go into P2O5. And this P2O5 will get into the slag. It will form P2O5 and it will get into the slag. And very important, carbon. The high amount of carbon in the hot metal, it will also take up the oxygen and it will form carbon monoxide or carbon dioxide depending upon the temperature. What is the temperature of the converter? Okay. So all these reactions that we have written here, all these reactions are basically uh, exothermic reactions, right? And that is what makes the steel making process autogenous, because these reactions are only involved. Now we will see that what happens. Suppose if I talk about the Ellingham diagram, we now know that what is Ellingham diagram. So let us briefly talk about Ellingham diagram and understand the main thermodynamics behind it. So I'll not draw the entire diagram. So along the x-axis, we have the temperature, and along the y-axis, it is the delta G of formation, okay, of the metal oxides. So if you draw this Ellingham diagram, okay, you will see that most of the lines of the metal oxide, say for example, if I draw the line for silicon, Si plus O2 getting converted to SiO2. So this is the silica line. Okay. After that, we have the manganese. So this is MnO line, I'll say. So this is the MnO line, followed by the phosphorus line is there. So this is the phosphorus line for P2O5, I'll just say. Likewise, we have the iron line for FeO, you can say, something like this. Okay. So these are the lines. But one line is there, which these all have the slopes in the upward direction. So these are positive slopes. All the metal oxide lines are having positive slopes. But there is one line which is having a negative slope, which is this red line that I have drawn. And what this red line is all about? This is basically carbon plus O2, 2 times of Cu. Okay. So this is the CO line. Now what happens when the temperature is higher? Suppose you see what is going to happen is that at high temperature, okay. So when the temperature is less, suppose this is the temperature at which this carbon CO is cutting the SiO2. So I can say that what will happen when the temperature, so suppose this temperature is basically our 1200 degrees Celsius. Now, at temperature greater than 1200 degrees Celsius, Okay. First, oxygen is going to take up the silicon. First, oxygen will take up the silicon. Okay. Because you see, at this temperature, what is happening? Our silica line is more stable compared to the MNO line because it is at the lowest position. The silica line is at the lowest position. So it's this metal oxide line is most stable. So silicon will first take up the oxygen. Okay. So first oxygen, I can say first oxygen will take silica. Okay. And make SiO2. And it is going to make SiO2, which is silicon dioxide, which is silicon dioxide or silica. As SiO2 is more stable compared to other oxides in the Ellingham diagram. Okay. Now, after that, what happens? Okay. So this part we have seen. Now, after that, let us focus what happens. Now, if I talk about the various reactions that are taking place, let us see the various reactions that are basically taking place. So we have the converter here. Like this. Okay. And we also have the hot metal. This is the hot metal. And on the top of the hot metal, we have the slag. Right? On the top of the hot metal, we have the slag. So this is our slag. Right? Now, the reactions that take place. Let us see the reactions. So oxygen, when we are blowing in oxygen, because there is oxygen lancing, so we are blowing oxygen. So oxygen will first get dissolved into the melt. So this is oxygen in the gaseous state. It is dissolving in the melt. So we call it dissolved oxygen. Right? So this is the dissolved state. Oxygen in the dissolved state. Right? Now, after that, what is going to happen is the carbon of the hot metal, it will take up this oxygen, this dissolved oxygen, and it will form CO, right? So this reaction is something which is very, very important, and we call it gas metal reaction. This is gas metal reaction. Why gas metal reaction? You understand it. See why this is gas metal reaction. Because the carbon is in the hot metal. The carbon is in the hot metal. And this oxygen, this can be dissolved. It can actually take place in two ways. One is it can be dissolved in the hot metal, or it can be directly in the gaseous phase also. So if it is in the gaseous phase, then the hot carbon from the hot metal is basically reacting with the oxygen in the gaseous phase and giving us CO, which itself is a gas. So that is why we call it gas metal reaction. Right? So rather than calling this gas metal reaction, it will be good if you call, let us one. So one is, this is the This is in the metallic form only. So let us not call it gas metal reaction. The same reaction, it can take place in this form. Like I can say that half of oxygen, this is in the gaseous form, is combining with carbon, which is in the hot metal. And it is basically giving us CO. And this we can call as gas metal reaction. Okay. Apart from that, what are the reactions that are possible? Other reactions that are possible. The carbon of the hot metal, it can also react with FeO. Where the FeO is coming? Obviously, you see some amount of iron will basically take up the oxygen. Some amount of iron from the hot metal will take up the oxygen, because when we are blowing in oxygen at high temperature, definitely you see at high temperature, what happens is the metal oxides, depending upon their del G value, that is the gives free energy according to Ettingham diagram, they will pick up the oxygen at high temperature. So the iron is also going to pick up the oxygen and get converted into FeO, which is the iron oxide, and this FeO will go into the slag. At times, this is called metal loss. Why we call it metal loss? Because ultimately you are losing the iron. Okay, this is important. At sometimes it is important, but when a lot of iron, if it goes into the from the hot metal, if it goes into the slag, that is not something which is good. So we will see that. We'll see that. So carbon from the hot metal, it can react with the FeO in the slag, and it can give us basically CO, that is the carbon monoxide, plus Fe. So this is basically slag metal reaction. This is slag metal reaction. So you can see that there are various interfaces at which my reaction can take place. One can be the gas metal reaction, one can be the slag metal reaction. So these are the various reactions that can actually take place. Okay. So oxygen plus iron. So oxygen, dissolved oxygen. Okay, this is the dissolved form. Plus the iron from the hot metal. So it will get converted to FeO. Okay. This is also basically our gas metal reaction. This is also our gas metal reaction, because this is dissolved oxygen. Now this dissolved oxygen can be also gas also. So iron is picking up the gas, that is the oxygen, which is in the gaseous state, and it is forming FeO, which is getting into the slag. So we can call it gas metal reaction. Right. Now we will see one interesting thing. Out of all these reactions, now I will ask you to focus on mainly this reaction, which is this reaction. Carbon is taking up the oxygen and getting converted to CO. Right? Now, if we just focus on this reaction, that is carbon taking up the oxygen and getting converted to CO. Okay. Typically, suppose the temperature we have given is basically 1600 degrees Celsius, because this reaction will take place at high temperature. And this is typical steel making temperature. Like I said, that most of the oxidation reactions are in exothermic. So as they are exothermic, so the temperature is going to be very high in this steel making. So if you look at this reaction, I can say that what is the equilibrium constant of this reaction? We can say it is nothing but partial pressure of CO followed by the activity of oxygen and multiplied by the activity of carbon. Right? Now, if the partial pressure is 1 atmosphere. If we maintain it as 1 atmosphere, because this is gaseous, so we can say that, then we can say that it is nothing but weight percentage of oxygen. So this is the constant, reaction constant, that is equal to 1 by weight percentage of oxygen into multiplied by the weight percentage of carbon. Okay, I can say this. Okay, now from here, one thing we can actually say, a very, very important conclusion we can draw from this. This is something very important. Okay, so please note this. If I call this equation 1. So from this equation, what we have derived, we have seen that it is weight percentage of oxygen multiplied by weight percentage of carbon, right? Now, this tells us that at equilibrium, if temperature is given to us and the pressure is constant, so temperature is basically, it is 1600 degrees Celsius, right? And the pressure is, we are maintaining the pressure constant, 1 atmosphere. Then the weight percentage of oxygen into the weight percentage of carbon, this is basically constant. This is constant. What it means? It means that from here we can also write that the weight percentage of oxygen is proportional to 1 by weight percentage of carbon. It means that when the weight percentage of oxygen, or when my oxygen percentage is increasing, my carbon percentage will decrease. Or when my carbon percentage will increase, my oxygen percentage will decrease when I am maintaining constant pressure and temperature. If I am maintaining the temperature to be 1600 degrees Celsius and the pressure is 1 atmospheric pressure, then I can say this. Right? So if I now draw a diagram, a plot, where I will here plot the oxygen, weight percentage of oxygen, or the oxygen concentration. And here I am going to plot the carbon concentration. This is going to be a hyperbolic graph, something like this. Okay? This is going to be a hyperbolic curve. What it means, you see, what this hyperbolic relation is actually giving you, what it means. It means that when you are increasing the oxygen blowing, initially see, before I start the process, the physical meaning we need to understand. It is very important. So before I start the process, the oxygen amount of the oxygen in the melt was very low. In the hot metal, the amount of oxygen was very, very low because I have not started blowing the oxygen. I have not started blowing the oxygen. So the oxygen is now very low. Now, when I start the process, then my oxygen is just starting, is just the percentage of oxygen is increasing. But when my oxygen was very low, at that time, you see the concentration of carbon was very high. So carbon, obviously in the hot metal, before I start the process, it is about 4%, 4%, something like that. So it is very high. But once the oxygen percentage increases, or the concentration of the oxygen increases in the melt, you see, once I am going up, like the concentration of oxygen is increasing, the carbon is decreasing at a very high pace, I can say. The carbon is decreasing at a faster pace, very, very fast pace. The carbon is decreasing, right? As I am increasing the oxygen, you see when the oxygen is increasing, as so localized carbon we are getting decreasing. So if the oxygen is here, the carbon is here. Okay, something like that. So it is evident from this graph. So as I am blowing with more and more oxygen, I am blowing in, actually decarborization is taking place. Okay, so that is exactly what this graph means. Okay, now we have seen this. Now let us focus on another reaction, which is basically, which is also taking place, and we let us consider this is a, basically this is very important, and this is a slag metal equilibrium reaction. Slag metal reaction. Uh, Fu, which is iron oxide, it is in the slag. So Fu is in the slag. When it reacts with carbon from the hot metal, the carbon is in the hot metal. Okay. This also oxidizes the carbon. Okay. So carbon is basically getting converted to CO. So, and FeO is getting reduced to Fe. When the FeO is getting reduced to Fe, it is getting back into the hot metal. Okay. So FeO, when it is in the FeO form, oxide form, it is in the slag. Okay. But when the FeO is getting reduced to Fe, it will definitely go into the hot metal. And this is our CO gas. So this reaction, if I ask you to concentrate. So what is the equilibrium constant for this reaction? The equilibrium constant for this reaction is going to be partial pressure of CO divided by the weight percentage of carbon into the weight percentage of FeO. Fe, right? I can say this. Okay. So here also, if I maintain the partial pressure to be constant, partial pressure of CO to be 1 atmosphere, if I maintain this, and if the temperature is also constant, temperature is also constant. Okay. Then I can say that this K value is going to be constant then. Okay. Equilibrium reaction, this K equilibrium for this reaction is going to be constant. Now, then I can say that from here that the weight percentage of carbon multiplied with the weight percentage of oxygen, sorry, this was our previous reaction. So this reaction I can say that the weight percentage of carbon multiplied by the weight percentage of FeO, okay, that is equal to some constant, and that value is nothing but 1.25 into 10 to the power minus 3 when the temperature we are maintaining at 1600 degrees Celsius and the partial pressure of CO is basically 1 atmosphere. Right. Now from here, if you draw a similar plot, something like this, and here you are taking basically what? Here you are taking the FeO content, FeO content, and here you are taking basically our carbon percentage, carbon. Okay. So similar kind of hyperbolic graph you will get, which means that when my FeO content is increasing, my carbon content is going to decrease. Why? Because the carbon will take up the oxygen from the FeO, because you see what happens. Try and understand the physical meaning also. This is also important. So when I will blow more and more oxygen into the system, suppose this is my hot metal. Now, when I blow more and more oxygen, so initially oxygen percentage is less. But when I keep on blowing oxygen, One is the temperature is going to increase, because what will the oxygen do? The oxygen will take part in many of the oxidation reactions. Now, when the metals are getting oxidized and getting converted to metal oxides, that will definitely increase the temperature of the system, because most of the oxidation reactions are exothermic. We have seen them. So that will increase the system, the temperature of the system. Now, as the temperature of the system increases, the oxygen, more and more oxygen will also dissolve into the hot metal, because you see, what is dissolution? Means it is dissolving via diffusion only. Okay, it is dissolving via diffusion only. And diffusion, we know that diffusion is a function of temperature. So if my temperature is increasing, the diffusivity is increasing. So more and more oxygen will diffuse into the hot metal. So initially, though in the hot metal, the oxygen content was less. But finally, what is going to happen? A lot of oxygen will eventually come into this hot metal. And inside the hot metal, iron is there. So if oxygen now comes, iron will pick up the oxygen and it will get converted to FeO. And FeO, once the iron is getting converted to FeO, the FeO will go into the slag. FeO will not stay into the hot metal. It will go into the slag. Now, when the FeO content increases, so that means with more and more blowing of the oxygen, my FeO content is also increasing. Now, when the FeO content increases, what happens? Apart from the oxygen, the FeO will also act as an oxidizing agent. So, FeO will also oxidize the carbon. So, when more and more FeO is generated, okay, so FeO also helps in decarburization. Okay, so you can write FeO also helps in decarburization, right? This is important. Now we will look at the different reactions one by one. Let us first talk about the silicon oxygen reaction. Let us first talk about the silicon oxygen reaction. So if I talk about silicon oxygen reaction, this is Si plus O2 getting converted to SiO. Okay. So O2 gas, I can say, is getting converted to SiO and it is going into the slag phase. Okay. This is basically, I can say this is gas metal reaction. This is gas metal reaction. Now, apart from that, we can also have the silicon in the hot metal. Silicon, it can also get oxidized by the FeO in the slag. Okay. And it can get converted to SiO2. SiO2 will go into the slag and iron will come back in the hot metal. So this can also happen. This is slag metal reaction. Because slag is reacting with the hot metal, so we have slag metal reaction. This is slag metal reaction, right? Anyway, the important part is silicon is getting converted to silica SiO. Okay, this is it. Now, silicon has got a lot of affinity. Silicon has got a lot of affinity towards oxygen. So silicon is going to be one of the impurities in the hot metal which will oxidize first, which will pick up the oxygen very fast. Okay. And silicon will go into the slag phase. But apart from silicon, our slag will also have some of the major constituents. Let us see. What are the major constituents of slag apart from silica? So major slag constituents. What are the major slag constituents? Apart from silicon, the slag will have a substantial amount of FeO. It will also have SiO2 and it will also have CaO, calcium oxide. If the slag is basic stuff, we are adding flux. So anyway, the slag will have this as the primary constituents. Right? Now, when pure SiO2 is there and there is no CaO, suppose I am talking about a slag which is we haven't added any flux. Uh, so we haven't added any lime, that is CaO. So at that time, what happens? At that time, what happens? The silica is the activity of the silica in the slag is going to be very high. So because I can say when pure silica SiO2 is there, and there is no CaO, there is no CaO, calcium oxide. Then what happens? The activity of SiO2 is nearly equal to 1. That means it is very high. Okay. But as we add lime, as we add CaO, what happens? In basic steel making process, the CaO, that is the calcium oxide, will capture silica. It will capture silica, that is SiO2, and activity of SiO2 will decrease. So activity of SiO2 will decrease in the slag. Now, when the activity of SiO2 is, why, first and foremost, let us understand why it decreases, because CaO or the calcium oxide, it captures silica. It forms CaO.SiO2. So you see the SiO2 is being captured. Okay. It is fixing up the SiO2. So definitely the activity of SiO2 or the silica is decreasing in the slag. So more and more, so this reaction, silicon plus oxygen getting converted to SiO2. If the activity of SiO2 is decreasing, then this reaction is going to be more in the forward direction. That means the more and more silica is going to be generated. That means more silicon will pick up oxygen and get into the slag phase. So in the note, you can write removal of silicon. Removal of silicon is not of much difficulty. It is not of much difficulty. Removal of silicon is not of much difficulty in basic steel making process. In basic steel making process. Okay. Because the addition of CaO, the activity of SiO2 is going to decrease, because with addition of CaO, the activity of SiO2 will decrease. Okay. And so the reaction is driven in the forward direction. Driven in the forward direction. Which reaction I am talking about? We are talking about this reaction. Okay. So it can be silicon plus FeO getting converted to Fe plus SiO2 also. Anything, but it is taking a box. This reaction, no problem. Right. So this was about the silicon. Now, let us see the manganese reaction. Now we will talk about the manganese reaction. Now, if I talk about manganese reaction, what it means? Mn, manganese, hot metal, in the hot metal. Okay. It can react with FeO, which is nothing but the iron oxide in the slag. And manganese, the FeO is going to oxidize the manganese and it will make MnO. MnO will go into the slag plus iron is going to be produced. And iron will come back into the hot. Right? So what kind of reaction it is? This is basically a slag metal reaction. This is a slag metal reaction. Right. Another thing which can happen in case of manganese reaction is carbon from the bath, or you can say also hot metal. It can react with the MnO. This is manganese. So see, manganese from the hot metal is getting into the MnO. So now the slag has MnO. Now the carbon can actually react with the MnO and it can basically form CO plus again the manganese will come back into the hot. So these two reactions are possible in case of manganese reaction. Right? Now the thing is when manganese, this is like manganese is taking up the oxygen from the slag and it is in the process it is getting into the slag phase which is the Mn and iron is reverting back or iron is coming back into the hot metal. Right? Now this is number one. This reaction is taking place something like this. And another thing which can happen is the MnO, that is the manganese oxide of the slag, right? The manganese oxide which is in the slag, okay, it will come in contact with the carbon, okay, in the bath, and that is going to produce CO. That is going to produce CO, like which is nothing but our carbon monoxide plus Mn, right? Manganese. And this manganese is getting back into the hot metal. Now, manganese in steel, we will not try to remove a lot of manganese because manganese in steel, it leads to solid solution strengthening. Leads to solid solution strengthening. So, too much manganese we will not like to reduce. Okay. But as manganese is having affinity towards oxygen, so definitely, and from the Ellingham diagram, we see that MnO line is just slightly lower compared to FeO line. So when FeO is getting oxidized, so manganese will also get oxidized at that time, at the operating temperature. Okay. So this is the manganese reaction. And if I now concentrate on the manganese reaction, solely on the manganese reaction, like Mn from the hot metal, it is coming in contact with the FeO of the slag. Okay. And what we are getting? We are getting Mn slag in the slag plus iron. If this is the hot. Right? Now, what happens? You see, if I try to talk about the K equilibrium of this reaction, it is nothing but the activity of MnO, I can say I can just simply say this is nothing but the weight percentage of MnO divided by the weight percentage of FeO multiplied with the weight percentage of manganese. Okay. Now, from here we can say that if I try to keep the weight percentage of MnO and weight percentage of Mn in one side, so I can say the weight percentage of MnO divided by the weight percentage of Mn, manganese. This is equal to K equilibrium into weight percentage of FeO. This we can say. Okay, so this is very, very important. The conclusion that we will now draw. So please note it. This is very important. What it means is that at a particular temperature, so when my K equilibrium is constant for this reaction, when my weight percentage of FeO is increasing in the slag, then my ratio of weight percentage of MnO by the weight percentage of Mn is increasing. This ratio, why it is special? Because you see this weight percentage of MnO, it is basically telling us what? It is telling us that what is the weight percentage of manganese which is in the slag phase, followed by the weight percentage of manganese which is in the metal. So this kind of ratios we call partition coefficients. They are called partition coefficients or partition ratios because they are actually telling us that what percentage of manganese is in the slag followed by what percentage of manganese is in the hot metal. So I can say this is LMN. LMN will stand for the partition ratio of manganese, and LMN is nothing but this. Whatever we have, weight percentage of Mn divided by the weight percentage of manganese. Yeah. So LMN or the partition ratio of manganese is equal to, it depends on, is directly proportional to weight percentage of Fe. So I can say weight percentage of Mn by weight percentage of Mn, that is the manganese. This is directly proportional to weight percentage of Fu in the slag. So when the weight percentage of Fu in the slag is increasing, that means more and more manganese is getting into the slag. Okay. So in the basic steel making process, CaO is also present. Okay. CaO is also present. And it increases the activity of manganese in the slag, as manganese would not like to be in the slag with CaO. So, okay, that part we will see a bit later because we'll just mix up it here. So here we will focus first on in this part. Let us. So as weight percentage of FeO in the slag is increasing, more and more oxygen we are blowing. That means weight percentage of FeO in the slag is increasing. That means more manganese is getting into the slag from the hot metal. Right? So this is exactly what is happening. And now we will see what is the effect of manganese reaction on the basicity, like on the basicity of the slag. On basicity of the slag. This we will see. Now in basic steel making process, you already have a lot of CaO, okay, in the slag. And CaO, what it will do? CaO increase the activity. It increases the activity of MnO in the slag. CaO, it increases the activity of MnO in the slag. It increases the activity of the MnO in the slag, as MnO would not So let us see. So CaO, it increases the activity of MnO in the slag, right? And as it increases the activity of the MnO in the slag, what is going to happen? That means if I talk about this reaction, the manganese reaction, which is Mn plus FeO, giving us MnO plus Fe. Now, if more and more, if the slag basicity is more, if the slag basicity is more, that means it is increasing the activity of MnO in the slag. This is the MnO, and this is increasing the CaO is increasing the activity of the MnO in the slag. That means this reaction is going to be in the this reaction will go more in the left hand side because the activity of MnO has increased in the slag because of the presence of CaO. So the more manganese in the basic steel making process, we will have more manganese in the hot metal when the basicity of the slag is increasing. So I can simply say that if I draw a plot, a graph, where we are showing here weight percentage of MnO, manganese oxide, divided by weight percentage of Mn. And here I am plotting, suppose the basicity, slag basicity. So this is basicity having basicity 2, and this is having basicity 4. So you can very easily see, and this is suppose weight percentage of FeO, weight percentage of FeO. Hmm. So you can very easily see from here that as the basicity is increasing, my MNO, weight percentage of MNO is decreasing. So the manganese in the slag is decreasing. So as the basicity of the slag is increasing, as the basicity of the slag is increasing, the manganese in the slag is decreasing. Okay? And vice versa. This we can basically say from here, right? Okay. Now, after this, we will simply see a very important reaction, which is another reaction we'll be discussing about, which is our sulfur reaction. Now, you see, in the iron making process, if I'm talking about the iron making process, in the iron making process, what happens? If I give, this is iron sulfide, we have to add CaO, which is the slag, in the slag, and iron making process means there has to be carbon, which is giving us the reducing atmosphere, carbon from the coke, and you will get FeO, sorry, you will get Fe plus CaS plus Ca. Okay. So this Ca is the carbon, sorry, calcium oxide. The calcium oxide will fix up the sulfur. Okay. Now, what is going to be the reaction in the steel making? What is going to be the reaction in the steel making? In the steel making, if we talk about the reaction, it is going to be FeS. Okay. This FeS is in the hot metal plus CaO. The CaO will come from the slag itself. So we will have FeO plus CaS, right? This is the slag metal reaction, and it is the steel making reaction, right? Now, try and understand that as the percentage of carbon is falling in the steel making continuous, then FeO is already there in the slag as O2 is injected. So this reaction is not driven in the forward direction much, right? This reaction will not be driven much in the forward direction. We see that in the oxidizing environment, as the formation of CO gas is there, okay, in the oxidizing environment, okay, as the formation of the CO gas is not there, the desulphurization process is becoming very difficult. So desulphurization process is very difficult in the steel making process. Right? So this is important. Okay. Apart from that, we should be talking about the dephosphorization reactions. Now, when I'm talking about the dephosphorylation reaction, you see the hot metal, if I say hot metal, the hot metal contains about 0.15 weight% phosphorus. Okay, this is the weight percentage of phosphorus in the hot. But the target level of phosphorus is we want to achieve 0.003 percentage of phosphorus. Okay, so a lot of dephosphorization has to take place. So when I talk about the dephosphorization, you need to understand dephosphorization is basically it is going to be it will move forward if I give it oxidizing atmosphere and basic atmosphere. So dephosphorylation requires, you can say, number one, oxidizing condition. So oxidizing condition, so no problem, because steel making is an oxidizing condition only, and basic atmosphere. So that means basic steel making process is actually good for dephosphorization. Okay, so you see that both these are not much problematic as far as the steel making is concerned. So we can achieve dephosphorization in case of our primary steel making process. But this cannot be achieved in case of desulfurization, because desulfurization requires reducing condition. Okay, and steel making is basically oxidizing. That is the main problem. Okay. Now, I said that dephosphorization, it requires oxidizing condition and basic atmosphere. So let us see. So suppose I have the phosphorus in the melt. It requires oxidizing condition. So it requires oxygen. Okay. Plus it requires basic atmosphere. Basic atmosphere means it will require O2 minus ions. Because basic atmosphere means what? Calcium, if I'm talking about CaO. So CaO is going to dissociate into Ca2 plus O2 minus. So O2 minus, the presence of O2 minus ions is actually going to tell you that the atmosphere is basic. Okay. So we can say that it requires this. Ultimately, what we will get PO4 3 minus. Okay. So I can say the equilibrium, K equilibrium, as the activity of PO4 3 minus square divided by the activity of phosphorus into the activity of oxygen to the power 5 to the activity of O2 minus to the power 3. I can say this. Now, I can say that activity of PO4 3 minus whole square divided by weight percentage of phosphorus in the metal. Okay, that is equal to K equilibrium, activity of oxygen to the power 5 and activity of oxygen to the power 5, activity of O2 minus. So this is whole square I'm talking. Right? We can say like this. Now, this is nothing but the partition ratio. You see, this is the partition ratio or the LP, because this is nothing but the phosphorus in the slag. This is the phosphorus in the metal. So I can say that when I'm talking about the partition ratio, then this is how it is dependent. And from here also, I can say one thing, that the partition ratio is going to be more if if it is basic, and if the atmosphere is oxidizing, because this is to the power 5 and this is to the power. So this is basically giving you basic. It is telling you that it is basic, and this is basically oxidizing ions. Okay. So this we have concluded. But you see, during when we blow a lot of oxygen during the latter part of the steel making process, phosphorus reversal also takes place, and this is a big problem. So you can just write it here that during the latter part of the steel making process, during latter part of steel making process, during latter part of steel making process, phosphorus reversal phosphorus reversal takes place. So phosphorus from the slag, it comes back into the hot metal. Okay. Now we will see basically the now we will talk more about the LD process. Okay. So if I talk about the LD process, so let us now focus on LD process. If I talk about the LD process, so LD, the full form is, what is the full form? This is called the link and Donawitz. Link and Donawitz process. So this was basically, this process is named after two places. Okay, one is known as the link and another is Donawitz. So actually this process was first used there in Germany. So that is why this name was given, right? So that is why the name is given like LD. So it stands for link and Donawitz. So here in the LD process, this is basically basic oxygen steel making process. So you can write this LD process is nothing but it is a basic oxygen steel making process. This is basic oxygen steel making process. And it is most widely used in the method of steel production in modern steel plants. Now, what happens in this process? In this process, basically molten pig iron from the blast furnace, along with controlled proportion of scrap steel, is charged into the converter. So, in the converter, we will charge the some amount of pig iron, obviously, and along with the pig iron, we will also charge the scrap. So, scrap plus pig iron can be charged. Okay. And the converter lining is basically basic. So the converter lining is, this is basically basic, I can say, basic lining. So in LD process, you have the basic lining because it's a basic steel making process. And water cooled lance blows the pure oxygen. So there is basically oxygen lancing, and this is the hot metal. Okay. And this lance, oxygen is at supersonic speed, very, very high speed. So it is basically making a lot of, it is increasing the temperature quite a bit. Okay. So the lance has to be water cooled. That is why we are using water cooled lance. And apart from that, okay, The oxygen purity of the oxygen is also very high. It is basically 99% pure. Okay, so oxygen rapidly oxidizes the impurities. Whatever impurities are there, it rapidly oxidizes the impurities like silicon, manganese, carbon, phosphorus. Okay, it oxidizes them rapidly. And these oxidation reactions, they release huge amount of heat, which melt the scrap and maintain the temperature without any external heating source. So I think this is now quite clear what happens. The oxidation reactions, I can say oxidation reactions. The oxidation reactions, they release a lot of heat, which makes the process autogenous. Okay. Now, mm, as carbon gets oxidized, a large volume of CO gas is also generated. Okay, so because carbon is also getting oxidized in this process, so a large amount of CO gas or carbon monoxide gas is generated, creating a foamy slag. So the slag that is basically produced here in this process is basically foamy. A lot of foam this slag will have. So it produces foamy slag, I can say. This process produces foamy slag. Okay. So why? Because a lot of CO gas is produced, and this CO gas is basically making the slag foamy. Okay. And this foamy slag is very, very helpful because it protects the refractor. Because of this slag, you see the hot metal is not coming directly, because where this slag is present, wherever this slag is present, this foamy slag is present, it is protecting the refractory lining because the hot metal is not coming directly in contact with the slag. And another thing, it is also protecting this lance, because if you see through this lance, the oxygen we are blowing, but this foamy slag is covering the lance also. So the hot metal is not coming directly in contact with the lance. Because you see, hot metal, it has got a lot of impurities. So it is very reactive also. So if the hot metal comes in direct contact with the basic lining, refractory lining, as well as with the oxygen lance, there can be corrosion and such problems. So foamy slag is actually good. Okay. Now, what are the advantages of LD process? Advantages of LD process. Let us understand what are the advantages of the LD process. Pure oxygen is blown, so no hydrogen contamination in the steel. So one is pure oxygen is blown, so no this is nitrogen contamination. So no nitrogen contamination in the steel. Right? Apart from that, due to highly basic slag, efficient removal of phosphorus and sulfur. This is having efficient removal of phosphorus and sulfur, right? And better temperature control and refining process, you can say. better temperature control, and refining. Okay. So we have some basic oxygen steel making processes apart from LD processes. We'll discuss them also one by one. Apart from LD processes, some other basic oxygen steel making processes. Let us discuss some of the basic oxygen steel making process. One is obviously LD process. So this is LD process is a basic oxygen steel making process. Another is LD bath agitation process. LD bath agitation process. This is also very important. LD bath agitation process. We'll discuss it. Combined top and bottom blown oxygen steel making process. Combined top and bottom blown oxygen steel making process. And what else? You can have pure bottom blown oxygen steel making process. Okay. So lining of the LD processes, like I said, the lining of the LD process is basic. It is basically basic lining. So it should be magnesite or dolomite. Now, one important thing that I should talk about here, as far as LD process is concerned, in the LD process, there is a formation of lance skull. Formation of, why I am discussing it? Because sometimes if this is asked like lance skull is associated with which of the steel making processes, obviously they will not ask you what is lance skull or things like that. But they can say that lance skull is associated with which of the following steel making processes. They'll give you some of the options. You must know that it is associated with LD process. So what happens, see, during oxygen blowing in the LD converter, so a high speed supersonic oxygen jet. So suppose this is my LD converter, right? This is my LD converter. Now, this is the oxygen lancing. Now, high speed supersonic jet of oxygen is striking the, it is striking the hot metal. This is the hot metal. So when the high speed supersonic oxygen jet is striking the hot metal, so there is going to be a lot of splash. This you can understand. A lot of splash is going to be there. Okay. And this hot metal, the surface where it hits, it basically converts it into small spherical bubbles. And everywhere there is going to be these spherical particles or that is going to be inside the something like this, the hot metal spherical droplets. Okay, so we'll talk about it. Okay, but splashing is also very common. So the hot metal, it will basically come in direct contact, So because of the flashing, it will move here and there, and it will come in contact with the lance also. So on the top of this lance, it will solidify like this. On the top of the lance, it will solidify like this. Why it will solidify? The moment it comes in contact with the lance, it will solidify. Why? Because this lance is super cooled by there is also there is a cooling jacket also. Okay, outside the lance. Because oxygen it is blowing at supersonic speed. If we are not cooling the lance properly, the lance will get eaten up because of high temperature. So this phenomena is called our formation of lance skull, right? So I am again telling during oxygen blowing in the LD converter, a high speed supersonic oxygen jet it strikes the surface of the molten bar, causing intense oxidation, heat generation, and metal splash. Now, small droplets of molten metal and slag get thrown upward and they come in contact with the water cooled copper lumps. These flash droplets solidify immediately and stick to the lance. Okay. This protects the lance from intense heat. So this is basically very beneficial because it protects the lance from intense heat, right? Okay. Now, another thing which I should talk about in this LD converter is, see, when we are talking about this LD converter, I can move this oxygen lance according to my own wish. Like I can lower the lance, I can make the lance a bit more, I mean, according to my own wish. Lance नीचे भी कर सकते ऊपर भी कर सकते, right? So this is the thing. Now, if I am lowering the lance and making it very close to our hot metal, then what happens? Deeper penetration. So you can write lower lancing, lower lance, it will do deeper penetration. But the surface area is going to be less. Surface area is going to be less. Okay, surface area means the surface area in which basically the oxygen is coming in contact with the hot metal. But if the lance is not lowered, okay, if the lance is basically uh, higher, higher lance, higher lance is going to give you shallow penetration, but more surface area is covered. Okay, so according to our own wish, we can actually uh, give this, I mean, maintain this in case of oxygen lancing. Okay, this is the thing. Now, I will talk about the melt composition and how basically with time the impurities are removed. So this graph is very important. Try to, if you can, try to remember this graph. So this is the time of blown. Okay, in the LD converter I'm talking about. This is the time of blowing. So this is 0. This is suppose 5 minutes, blowing for 5 minutes. This is blowing for 10 minutes. This is blowing. Blowing means oxygen. I'm blowing oxygen. 15 minutes, and this is basically 20 minutes. Now, see, and this is our various concentrations of, I can say, of various impurities, like concentration of silicon, concentration of, you can say, phosphorus, concentration of manganese, and concentration of carbon also. So this is the silicon curve. This is silicon. Okay. So silicon will be oxidized in the first Most important, silicon will oxidize first. Okay. And then my manganese oxidation is going to start, but it will take time. So manganese oxidation, maybe I am showing in pink color. So it will take time. The slope is comparatively slower compared to silicon. Something like this. This is our manganese. Okay. Then how is going to be our phosphorus? You can say phosphorus will have some curve, something like this. Will come. At the end, it will become more or less constant. Okay. And last but not the least, our carbon. How our carbon will descend? This is how the carbon. So all the impurities with time, they will. So this is carbon and this is phosphorus. So the thing is, all the impurities are getting removed with time or getting oxidized with time. But you see, first that is removed very easily and very fast is silicon, manganese. Then carbon is reducing something like this, and then you have also the phosphorus there. Okay. Now we talked about bottom blowing oxygen steel making process. Now let us see what is the bottom blowing oxygen steel making process. Yeah. In the bottom blowing oxygen steel making process, if I talk about bottom blowing oxygen steel making process, if I talk about bottom blowing oxygen steel making process. So in this process, what happens is pure oxygen is blown from the bottom of the converter through refractory lined tuyeres. So you have so in the LD process, like oxygen was blown from the lungs, here we blow the oxygen from the bottom. So pure oxygen we are blowing from the bottom. But you see, as we are blowing the oxygen from the bottom, that will create a lot of heat. Why? Because immediately where the oxygen meets the hot metal, there the oxidation reaction starts. And oxidation reactions are extremely exothermic, so heat producing. So it will eat up the lungs. So the cooling system has to be very, very efficient. Now, in the bottom blowing oxygen steel making process, the cooling system is not like we are cooling it by water. It is not like that. We have a specialized cooling system, which is hydrocarbon is often used as cooling and protecting the gas to prevent liver damage. So we use basically hydrocarbon. Hydrocarbon is used for cooling. So why hydrocarbon or how hydrocarbon is used for cooling? So see, you have this is the clear. Suppose from here we are blowing the oxygen. In the side, we will have hydrocarbons. These are the channels for hydrocarbons. These are the channels for hydrocarbons. Now, what happens as hydrocarbons are going through these channels, and in the middle, oxygen is going, by the side channels, hydrocarbons are going. Now, cracking of hydrocarbon takes place at high temperature because oxygen is blowing in the middle channel, and this is basically making this is basically increasing the temperature. So, by this in the side channels, cracking of hydrocarbon starts. Okay, so cracking of hydrocarbon takes place, and cracking of hydrocarbon is endothermic reaction. Cracking of hydrocarbon is endothermic reaction. right? So this is basically endothermic reaction. So this protects the twears. It acts as a cooling jacket and it protects the twears. This kind of twears, they have got a specific name. They are basically called Savard Lee twears. Okay, they are called Savard Lee twears. So this is all about the bottom blowing process. Another process that I should discuss is what we call the bath agitation process. Now, this process is just the same as the LD process, nothing much, just one addition. That is, this is the lance, this is the converter. This is the converter. This is the oxygen lancing to which we are passing the oxygen. This is the hot metal. Okay. And from the tweers, actually, what we will do, we will just blow argon. We will blow argon. We are blowing argon. So it is mixing this. You can understand one thing. Oxygen is whatever reactions are taking place that are because of the oxygen only. But as we are actually blowing the argon, it is mixing the hot metal uh, in a more efficient manner. It is mixing the hot metal in a more efficient manner, right? So there is superior mixing and bath dynamics, I can say. Right? Higher decarbonization efficiency because of better mixing. There is higher decarbonization efficiency. Right? Better phosphorus removal is there. Right? So these are some of the advantages. Okay. Now we talk about a very important topic, which is the deoxidation of steel. Deoxidation of steel. We talk about it. So let us see what is deoxidation of steel. So see, when molten steel is tapped from the converter or EAF, whatever it is, okay, it contains dissolved oxygen, which can cause basically blowholes or porosity or oxide inclusions or see oxygen, if oxygen level is too much high in the molten steel, okay, or in the hot metal, that is something not good. So the oxygen is going to create a lot of problems. So we need to deoxidize this steel. So what are the problems? Let us first emphasis on that. Problems caused by excessive oxygen in the steel. Please write it. Problems caused by excessive oxygen in the steel. So what are the problems? Blowholes or porosity. So this can be one of the problem, which is blowholes or porosity. Oxide inclusion. oxide inclusion can be a problem. Then poor ductility and toughness. So these are all the problems that are caused by excessive oxygen in the steel. So the idea is that we need to deoxidize the steel. Okay. Now you can ask us one question, that why the oxygen is coming in the steel. Now you know that steel making is basically a oxidizing process. So in the steel making itself, we have seen in the process itself, like in the LD converters and all, in the BOF or the LD converters, all the processes we have talked, we are directly uh, charging the oxygen. So oxygen will obviously come into the hot water, right? But this oxygen has to be removed. How this oxygen is removed? The main principle of removal of this oxygen is how it is removed. We add strong deoxidizers. We add strong deoxidizers. We add very strong deoxidizers that have higher affinity for oxygen than iron. Higher affinity for oxygen compared to iron, right? So uh, let us basically name some of the deoxidizers and what are the oxide they are forming. Okay. So if I'm talking about aluminium, aluminium is a very strong deoxidizer. Now from the Ellingham diagram itself, you can basically see the deoxidizers from the Ellingham diagram itself. Okay, so aluminium is the deoxidizer, and what is the oxide forms? It is Al2O3. Silicon, what is the oxide form? SiO2. Okay, that is the oxide which is formed. Say for example, similarly, Mn, manganese, if I am talking about, it is forming Mn. Okay, calcium, if I am talking about, it is forming Ca. Likewise, titanium, zirconium, they are forming stable oxides. But the thing is, we just understand that aluminium and silicon are widely used, and we'll be talking about aluminium and silicon. You can also check which is a strong deoxidizer whose oxide is going to be stable. So from the Ellingham diagram, you can itself say that those oxides which are lower in the Ellingham diagram, okay, they are all stable oxides. So all of them have the property to actually uh, form strong deoxidizers. Okay. Now, price is another consideration, obvious. And aluminium and silicon are fulfilling all the criteria. So, aluminium and silicon we will be using. Okay. Silicon, we basically use, we do not directly use the silicon. When we use the silicon as a deoxidizer, we use it in the form of ferrosilicon. So, ferrosilicon is added. Right? So, this is the part. Ferrosilicon is added. Now, with this we have substantially covered our primary steel making process. Now we will start our secondary steel making process. Okay. So secondary steel making itself is also very, very important. Okay. So we'll talk about secondary steel making process. Now, secondary steel making, it is sometimes also called the ladle metallurgy. Okay, it is a critical refining stage that occurs after the primary steel making and before basically casting. Okay, when steel comes out of the blast furnace, of the BOF, that is basic oxygen furnace, or the EAF converter, it is called crude steel. So the steel that we are actually getting from the BOF, which is coming out from the BOF, we are actually getting crude steel. So this steel needs to be refined. More refining is basically is needed. So crude steel, although most of the unwanted impurities, like if I'm talking about carbon, silicon, phosphorus, and part of sulfur, these are already removed in the primary unit. But this crude steel is having O2, H2, and N2. And sulfur is also there, sulfur. So these impurities are quite high in the crude steel, which requires basically further refining, right? So that is why that is the main idea of the secondary steel making process. Okay. Now, when I talk about the secondary steel making process, so ladle ladle is the basically heart of secondary steel making process. That is why the secondary steel making process is also known as ladle metallurgy. Okay. Now you see, uh, mainly what is happening in the secondary steel making process, desulphurization is very effective here because this desulphurization is very effective in the ladle. Because why? I tell you, desulphurization. This is mainly done in the secondary steel making process. Okay. So if I talk about desulphurization, it is very effective in the ladle furnace. I can say that desulphurization is very effective it is very effective in the ladle furnace. So this is very effective in the ladle furnace. And what is happening as the slag is highly basic, as the slag is highly basic, okay, by the addition, why it is highly basic? Because we have added lime. Under proper study, sulfur from the molten steel reacts with the slag. So if you are properly studying, the sulfur from the molten steel reacts with the slag. It reacts with the slag, right? Forming oxides. and transfers into slag as calcium sulfur, right? So this is something which happens. Now we can see that, okay, obviously in the ladle we can deal with this high amount of sulfur. Okay, so in the secondary steel making process this can be done, but not only sulfur is the not only the problem. There are some other problems also that we need to understand. What are these problems? What are the other problems? Like there can be more amount of uh, hydrogen, there can be more amount of nitrogen or even oxygen. Okay. Now, if their amount is more, how to remove them? The process that is used here in the secondary steel making is what we call RH degassing. RH degassing. So this RH stands for Rusta. This is actually German word. Miracus. This is Rusta Hideous, hideous. Heraeus. So this is basically German word where it was first used. So this is called RH degassing. So what is happening in the RH degassing? We'll just overall we'll take, basically this is vacuum. This is also called as vacuum degassing. So you can, if you do not find the RH to be suitable, so you can also use this vacuum degassing. Okay. You can use this as well. This is nothing but vacuum degassing. Now, what happens in the vacuum degassing? Vacuum is basically used in order to remove the gaseous impurities like dihydrogen, nitrogen, oxygen. If their concentration is high, by employing vacuum, we will basically remove them. Okay, we will remove them by employing vacuum, right? So actually, what happens is this kind of system is there. I tell you, these are known as snorkels. Snorkels. So this is a chamber, and this chamber is basically now this is the ladle. This is the ladle, and in the ladle we have the hot metal, and these snorkels are dipped inside the hot metal. Now we are going to blow from this, we are going to blow argon. So there is hot metal, a lot of hot metal. Now when I am blowing argon, this argon will form bubbles, and a lot of argon will also pass from this nozzle. Okay. A lot of argon will pass. So this will take the hot metal along with it. Okay. So hot metal are also getting into this chamber. Hot metal are also getting into this chamber, right? So now what happens? This chamber is basically kept in vacuum. This is vacuum. So as this chamber is kept in vacuum, and when the hot metal is getting into this vacuum, then automatically the gaseous elements or the gaseous impurities like H2N2 and O2 that were there in the hot metal, they are basically removed. And this I can call as the up snorkel. From the up snorkel, the hot metal is getting into the vacuum chamber, and from the down snorkel, they'll come into the ladle, back into the ladle. So this is my pure steel. Just this is what is happening in the vacuum degassing system. Now let us, this is the secondary steel making process. Now let us see what is known as continuous casting. What is known as continuous casting? We'll see. Right. So if I need to see what is continuous casting. So continuous casting, it is a modern metallurgical process in which molten metal, which is typically steel, is basically poured continuously into a water-cooled mold and solidified as it moves through the casting equipments to produce long, uninterrupted strand with a constant cross section. Sometimes we call them billets, we call them looms, okay, or strips even, right? So what are, first and foremost, let us see what are the components of continuous casting. What are the components of continuous casting? So components of continuous casting are, one is the ladle. Okay. So ladle means it is a large steel vessel that receives refined molten steel from the secondary steel making. So you have the ladle. So this ladle is basically receiving the product of the secondary steel making. So whatever you have got from the secondary steel making, that you are pouring into the ladle, and it transfers the metal to the casting platform. So from the ladle, the metal is being transferred to the casting platform and controls the metal temperature and flow also. Okay, flow is basically regulated using slide gates. So in the ladle, we also have slide gate from which we are regulating the flow, or stopper rod is also there. You can just stop it. Okay. And argon purging is provided to keep the steel clean and prevent nozzle clogging. What is nozzle clogging? Nozzle clogging means from the nozzle from where the steel is going to come out from the ladle, it can clog. So if argon is there continuously, then it will prevent it from clogging. Okay. This is ladle. Second is our tundish. What is tundish? Tundish is a metal distributor which is located between the ladle and the mold. So suppose you have the ladle. I show you. So tundish, you always remember between ladle and mold. Tundish will always be there between ladle and mold. It maintains a constant head and supplies steel continuously and uniformly into the mold. So that is the main work of the tundish. What is the main work of tundish? Okay, it supplies uninterrupted melt into the mold. Into the mold. Right? So the main function of the tundish is, I can say, what is the main function? Right? It acts as a buffer reservoir. It acts as a buffer reservoir. It acts as a buffer reservoir and it avoids interruption during ladle charge. And this also removes non-metallic inclusions using flow modifiers. Using flow modifiers. Right? So this is the function of the tundish. Apart from tundish, we can say about the spray cooling. Spray cooling or the secondary cooling zone. Secondary cooling zone. So what is the function of the secondary cooling zone? After the mold, strand is cooled using water sprays to basically it has to be cooled to control the microstructure or minimizes the thermal cracks, right? So that is mainly the use of this spray cooling. Apart from that, we also had support rolls. Now the support rolls, they basically what it does, if rolls support the hot strand and force continuous withdrawal. Okay, say for example, you will understand it if I kind of draw this. If I draw this, then it is going to be more easy for you to understand. Suppose this is my ladle. So from the ladle, it is getting into the tundish. Okay, so this is the tundish. From the tundish, it is getting into, there are dummy burrs. And from here, this is my continuous casting mold. Okay. And these are the roles, support roles that we are actually talking about. Right. So see, these roles are rotating. These roles are rotating like this. Okay. And because these roles are rotating like this, they are withdrawing. There is continuous withdrawal of this section. Okay. There is continuous withdrawal of this section. And there will be sprayers in between these rolls only. There will be sprayers to cool this continuous casting. Okay. And there is a dummy bar. This is what we call a dummy bar. So what is the role of this dummy bar? This dummy bar, it is a reusable steel bar which is used during startup. That means during the starting operation, this dummy bar is basically becoming very, very important. And it gets attached to the initial molten steel. Okay. And after that, we will also cut the sections like by using torch cutting. So there are torch cutters also. Okay. So they will cut it into cut the various slabs. Okay. And apart from that, another very important is our mold flux. Mold flux. So mold flux means it is basically nothing but these are casting powders. Casting powders. Okay, these are applied on top of the meniscus because they help in lubrication between mold wall and steel. Lubrication between mold wall and steel. And it reduces heat flux variations also. So there are many properties of this mold flux. Let us see some of the important properties of the mold flux. So some of the important functions rather. So mold flux, important functions, you can say So lubrication between, it helps in lubrication between mold wall and steel. Second, reduces heat flux variations. Reduces heat flux variations, captures and dissolves the inclusions, protects from deoxidation, and it provides thermal insulation. So these are some of the functions which mold flux actually does, right? So with this, our continuous casting process is also, we have substantially covered it. So our steel making part we have already covered. I think that the lecture was really helpful, and stay connected with MetaGate for more such useful lectures in upcoming days.